Hello friends, welcome to the channel of Digital to Real. Today we are going to do the Verilog code of Booth's multiplier. आज हम किसका Verilog code लिखेंगे? आज हम Booth's multiplier का Verilog code लिखेंगे. Already in my previous video I have discussed about the Booth's multiplication algorithm. ठीक है? So now in this video we will go through the Verilog code and the logic how to write the Verilog code. Please refer to the video of Booth's multiplier which I will provide in the description so that you get to know in better way what is the Booth multiplier and then go through the Verilog code. Now here is the flowchart of Boolean multiplication algorithm. We will start it. We start the algorithm. A is the accumulator. It is a variable, okay, that will store the partial product of the multiplication. Q minus 1, it is also a variable. It will store the value of Q0 after every arithmetic shift right operation. But initially it would be put as 0. It is a variable. M will contain the multiplicand and Q will contain the multiplier, and count n. N determines the number of times the loop of the algorithm will run, and n is equal to the number of bits of the multiplier. So here is a decision making block. Q0, Q minus 1 are 2 bits. Q0 is actually the LSB of the Q multiplier. Q minus 1 is this bit. Initially it is 0, but every time the arithmetic shift right operation happens, so Q0 will move to Q minus 1. So these 2 bits we will concatenate together and we will check for whether it is 0, 1, 1, 0, 0, 0 or 1, 1. If these 2 bits are 0, 1, then what we are doing? We are updating the accumulator value. A would be updated as A plus multiplicand. A is the old value of A and this A is the new value of A. If it is 1, 0, then A is updated as A minus M, where A is the old value of A and this A is the, after the subtraction, is the updated value of A. But if Q0, Q minus 1 together make 0, 0 or 1, 1, in either of the cases, we will directly go here. We will do the arithmetic shift right operation here. Of what we will do arithmetic shift right? We will do the arithmetic shift right of A, Q, Q minus 1 all put together. Let it be that A is a 4 bit, Q is a 4 bit and Q minus 1 it is 1 bit. So all put together is 9 bits. So we will do the arithmetic shift right operation. So if it is 0, 1, as I said, we will go here, update the A and then again we will come to the arithmetic shift right operation block. If it is 1, 0, Q0, Q minus 1, we will do the updation of A and we will come to the arithmetic shift right operation block. In either of the cases, this case, this case, this case, obviously we are doing the arithmetic shift right operation, but here we are updating A, here also we are updating A. But here we are not updating A, we are keeping the value of A as it is. And please note, while doing the arithmetic shift right operation, every time the MSB, after doing the arithmetic shift right operation, the MSB of the A would remain same here. After the arithmetic shift right operation, whatever the value will come, no, the MSB bit will be vacant. That would be same as the old value of A. That MSB bit will remain same because that contain the sign bit. That contain the sign bit. We are doing the multiplication of signed number. Please note, after doing all these things, we are decrementing the count value. Okay. Initially the count value will be equal to the number of bits of the multiplier. I will decrement it and it would become count equal to count minus 1. This one is in continuation to what I said, the flow chart. So we will check for whether the count is equal to 0 after the decrementation of the count. If it is yes, then we will end the loop. We will come out of the loop and the multiplication would be done, and A and Q together they will hold the multiplication result. If it is not, if the count is not 0, then we will again go to the loop. You remember which loop? This loop. It will come from here, it will go here, it will again check for Q0, Q minus 1 value. Okay, then after this thing, ASR, then we will do the count value decrementation. We will again check for whether Q is equal to 0 or not. If so, we will come out of the loop. If not, we will again repeat the iteration. We will go through the loop. We will do the iteration. Okay. This is the flowchart of the Booth's algorithm. What is the logic behind the Verilog code? Okay. So Booth's multiplication is actually meant for sign numbers. What we multiply? The multiplicand and multiplier are both sign number. Okay. So the MSB of the multiplier and the MSB of the multiplicand actually carries the sign of the numbers. So what is the input to the Verilog code? We will have the clock input to the Verilog code. We will have the reset input to the Verilog code. We will give the multiplicand and multiplier operands to the Verilog code. We will have a start pulse so that we can start the FSM. Okay, that also to the Verilog code. What would be the output of the Verilog code? Main output is the product which will get, that is the output. And we will have another valid signal which shows that yes, the count has completed. Now the final output is available at the Z. Okay, so Z and valid are the two outputs of the Verilog code. Now in FSM, we will have two states. One state is the idle state, another one is the start state where actual computation will happen. So in idle state, what we do is that we wait for the start pulse. Once we get the start pulse, we move to the start state. In start state, what we do? We do the actual computation of the Booth's multiplier. That is, we check for the value of Q0, Q minus 1. Then we will do the ASR. Okay. Once we will update the accumulator value, then we will do the arithmetic shift right operation. Once that is done, we will decrement the counter and we will check for it whether it is 0 or not. Once it is 0, okay, we will go out of that loop. So upon completion of the counter, valid pulse is made high and FSM move to the idle state again. That means the data is now available, output is now available at the Z. So here is the module definition of the Booth's multiplier. Module Booth's mul means Booth multiplier. What are the signals to the Booth's mul block? Clock, reset, start, X, Y, valid and Z. Input is clock, input is reset, input is start, and operands are specially put as signed. They are signed numbers. X and Y are multiplicand and multiplier. So input is signed 3 down to 0, X, comma, Y, semicolon. In that 3 down to 0, the MSB carries the sign of X and Y. Output is also signed, output sign 7 down to 0, Z. So Z carries the product of X and Y, and this is also a signed bit number where the MSB carries the sign. There is another output signal, that is the valid output signal, output valid. Okay, single bit signal, semicolon. Now what we have done is that by default they are all actually wired type. Input and output are wired type. Now I have declared them as reg. So reg signed 7 down to 0, Z. So Z I have specially made it at registered type, which will carry the product value, comma next z, comma z temp, semicolon. So the next z, this is also 7 down to 0, and z temp, semicolon, it is also 7 down to 0. The next state and present state both are of registered type. Reg next state, comma present state, semicolon. Reg 1 down to 0 temp, comma next temp, semicolon. And reg 1 down to 0 count, comma next count, semicolon. So this one is 1 down to 0. What it does is actually, you remember the q and q0 and q minus 1, the concatenation of it, where we check whether it is 0 1 1 0 or 0 0 or 1 1. So temp carries that 2-bit value, and next temp is another temporary variable which is used in the FSM to carry the q0 and q minus 1 concatenation. Then count carries the number of bits of the multiplier. So 3 down to 0, 4 bits are there. So count would be 2-bit. 2 raised to 2 is 4. So count would be counting 0 0 0 1 1 0 1 1. This way the loop would be run for 4 times. And the next count is another of 2-bit value that would be used in the FSM. Then is the register. Valid is of registered type and next valid is of registered type. Wherever the next is used, no, they are all used in the FSM. Parameter idle is equal to 1 tick B0 semicolon. Parameter start is equal to 1 tick B1 semicolon. Okay. Now always at the rate of pausage of the clock, when the clock is pausage or negate of the reset, okay, begin. If not equal to reset, begin Z. Okay, non-blocking statement 8 tick D0 semicolon. So at the reset value, when the reset is 0, at that time I am initializing all the values to 0. Z 8 tick D0 semicolon, valid 1 tick B0 semicolon, present state 1 tick B0 semicolon, temp 2 tick D0 semicolon, count non-blocking, 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 non-blocking. All are non-blocking statement, non-blocking assignments. So in everywhere I am assigning 0 at the reset. So not of reset means it is 1 value. If 1, then this block will enter and this will get executed. Now else, if the reset is 1, at that time it will enter else statement and begin and block it will enter. Z non-blocking assignment, next Z. So next Z value will be assigned to Z. Valid non-blocking assignment is equal to next underscore valid semicolon. Present state non-blocking assignment next underscore state semicolon. Temp non-blocking assignment next underscore temp semicolon. Count non-blocking assignment next underscore count semicolon. So end is for this particular begin statement. Okay, there is another end. This end is for this begin statement. So after that we will enter another always block. Okay, always at the rate of star. Star means any of the values which are used in right hand side in this block of code, whenever they changes, this particular begin and block we will enter. Okay, so case present state means this is also variable. If the present state changes, we will enter this block. Okay, if it is 0, it changes to 1. If it is 1, it changes to 0. In either of the cases, we will enter this always block. Now there are two states. Now first of all, in the case statement, if it is 0, then it is idle. So inside the idle block, this is a label. Okay, idle is a label. In Verilog it is a label. So I enter this begin and block. Begin, and here is actually the end of that particular block. Here is the idle. We enter the idle state. Now what happens in the idle state we see? Inside the begin block, next count I am initializing it to 0, and next valid also I am initializing it to 0. If start pulse I get. So that also is a part of the sensitivity list. Present underscore state is a part of sensitivity list. Start is also a part of sensitivity list. Okay. So begin, inside the begin block, what happened? Next state would be equal to start. Semicolon. The parameter start we have put. Okay. So parameter start we have used, that is 1. Okay. So next state would be 1 tick b1 semicolon, and next temp would be x of 0. So xy, we consider x as the multiplier. So 0th bit of the multiplier, that is the LSB of the multiplier, comma 1 tick b0. This is for the q minus 1 bit. Okay, which we will concatenate and we will check for the value of 0 1 1 0 1 1 0 0. Okay, and we will do the updation of the accumulator, and then we will go to the ASR operation, that is arithmetic shift right operation, which I have discussed. Okay, so next temp x of 0 comma 1 tick b0 semicolon, and next z is equal to 4 tick d0 comma x z. That means 4 tick d0 means what actually? A and Q will together form the product, that is the output of the multiplier. So A is 4 tick d0, that we have put initial value of A, we have put 4 tick d0 comma x is the multiplier value semicolon. So this is the begin end. So when the start pulse we will get, what we will do? Q minus 1 we will put it as 0, and A also we will put it as 0. We have gone through the flowchart of the Booth's multiplication algorithm. Please go through it again. You will be able to understand that A and Q minus 1 we are initializing it to 0 at the start. Okay. Else statement in the idle state. Okay. If the start statement is false, that statement is false, then begin and statement will not be, begin and block we will not enter. We will enter this particular block where 3 statements are there. Next state is equal to present state semicolon, next temp is equal to 2 tick d0 semicolon, and next underscore z is equal to 8 tick d0 semicolon, end. Okay, this 3 statement we will enter. So this is the end of the begin statement. So this begin statement has an end, this one. Okay, in this begin statement what we were doing, first of all we need in next count and next valid we initialize to 0. Then if the start pulse is there, then only these 3 statement will execute. If the start pulse is not there, the next state is equal to present state, it would remain. Next temp is also equal to 2 tick d0, and next underscore z also 8 tick d0 will only remain. Okay, we will go out of the loop only when the start pulse we will get. Here we got the start pulse, no, and next state has become the start, so we will reach here. Now in the start state there is a case statement which will check for the temp value. Okay, temp value, the temp value, if it is 2 tick b10, then z underscore temp is equal to what it will do? So z value, that is the z, here is the product value is concatenation of A and Q. Okay, and A is what? If it is 1 0, no, A is equal to A minus M. So here M, that is the multiplicand, is Y, and X we discuss, it is the multiplier. So Y is the multiplicand, and Z 7 down to 4 carries the A. So A minus 1 is equivalent to Z 7 colon 4 minus Y comma Z 3 down to 0. We will concatenate it, and here is the semicolon. Next is the 2 big 0 1 semicolon. Next is 2 tick B 0 1 colon. So here it is one case statement. Here is the another case statement. Here I will do the addition actually. Temp Z underscore temp is equal to concatenation of first term in the concatenation is what? Z 7 down to 0 plus Y. That is A plus M we do, no? The same thing. So Z 7 down to 4 is actually equivalent to A. So A plus M, and Y is equivalent to M multiplicand, comma Z 3 down to 0. So Z 3 down to 0 will actually carry the Q. And here is the semicolon. And the default value is what? Z temp is equal to, means there would be no updation of the accumulator value. Okay, at that time there is no addition, plus Y and minus Y is happening. So Z 7 down to 4, comma Z 3 down to 0, they will together get concatenated and they would be put in Z underscore temp. Please note, always is a procedural block which runs parallelly. All the blocks in the Verilog code which are always, they will run at the same time. They will run simultaneously. They will run parallelly. This always block, where at always at the pause edge of the clock or neg edge of the reset, we check for the reset. If the reset is there, we initialize all the register values to 0. Okay, if the reset is not there, we initialize the register value with the next Z. Okay, and this always block, where we check for the present state in the case statement, whether it is idle or in the start state. Okay, and we go to the respective begin and block. So this always block and this always block, they both run parallelly at the same time. Now here is the next step when we are concatenating the Q0 and Q minus 1 bit of the multiplier. In our case, X is the Q, that is the multiplier. Now already once initially once the state machine has been run, okay, and after that we are doing X, we assume that once it has been run when the count was 0, okay, now we are doing the next set of updation of temp, that is X count plus 1, X of count, that is X of 1 and X of 0, okay, that we will check. And next count value will be incremented count plus 1 tick B1 semicolon. So you should know that here in the code, rather than decrementing the count and checking it 0, we are incrementing the count. Okay. Next Z, what it would be? Z temp value arithmetic shift right operation 1 semicolon. So this is arithmetic shift right operation. So this is the operation, that is the arithmetic shift operation. What it does, that is what is the speciality of this particular operator is that is preserve the sign of the MSB of the variable. Okay, it's preserve the sign of the MSB of the variable. So this is the arithmetic shift left where we keep the sign, and this is the arithmetic shift right where we keep the sign. And is actually a bitwise AND operator in Verilog. Next is the next valid where we are using this AND operator. You see AND, then the AND count conditional operator 1 tick B1 colon 1 tick B0 semicolon. So AND count means what? Count is a 2-bit. Okay, so what are the combination it will have? 0 0 0 1 1 0 1 1. So when the 1 1 combination will come, AND of count would be 1. So this particular statement would be true and the next valid would be 1. Okay, and the next valid is 1, that means is what? The next state would be again the idle state. We will come out of the start state, we will go back to the next state as idle. So here in both the cases we are checking for and count, and count. And count is 1. When this is 1, and count is 1, next valid would be 1, and the next state here also idle state. So this is the end and this is the end case. This end case is for this particular case. Case temp where we are checking for 2 tick B10 or 2 tick B01 or default state. So here for the temp, case temp. Okay, this is the end case for that. And this begin has an end. And there is the end module. That is the end of the design code. Now here is the test bench for the booth multiplier. So module booth underscore TB semicolon. So clock reset start. They are of reg type. X and Y the operands. Signed operands 3 down to 0. Y is the multiplicand and X is the multiplier. They are of reg type. Wire Z, that is also signed in nature, 7 down to 0. That will contain the product of X and Y, and that is wire in nature. So clock generation circuit always #5 clock equal to naught of clock semicolon. Now instantiating the boot module, boot mul instant clock comma reset comma start comma X comma Y comma valid comma Z bracket close semicolon. So this is the port list. Now we will go inside the initial block. Initial $monitor system task is called $time comma inside the double quotes I am checking for X equal to %d comma Y equal to %d comma valid equal to %d comma Z is equal to %d semicolon comma X comma Y comma valid comma Z semicolon. So X is equal to %d. That means whatever is the X is the Y is the X is the multiplier, Y is the multiplicand, that would be displayed. In valid, whether it is 1 or 0 would be displayed. Z would display the product value. Please note it is $monitor, means whenever any of the values, whether it is X, Y, valid, Z changes, anytime any of the value changes, this $monitor system task will be called and it would be, and this all the variables will be displayed. Their values at the $time would be displayed. This is the initial begin end statement where I am sending the actual multiplier and multiplicand value. Here multiplier 5, multiplicand 7, clock, 1 tick B1, initially reset, 1 tick B0, start is equal to 1 tick B0 semicolon. After #10 delay, reset is equal to 1 tick B1 semicolon. After #10 delay, start is equal to 1 tick B1 semicolon. After #10 start equal to 1 tick B0 semicolon. Okay. So here start has been made 1. Initially reset was there. All has been initialized to 0. All the variables in the code. Then the reset is made 1 and then start is made 1. Then the FSM of the code will be entered. Okay. From the idle state it would go to the start state. Okay. And when the valid is 1, we have made it as even. This variable when the valid is 1, this 2 statement would be executed. #10 X equal to -4 semicolon, Y is equal to 6. Means at valid what will happen? We will get the Z value. Okay, and that Z value would be actually displayed and the $monitor will be called. Okay, please note here no begin end statement has been used because it is only a single system task call $monitor. Now here it is @valid, that means Z is already available. Now we will, and the state machine has gone back to the idle state. Now we can send next set of multiplier and multiplicand value. #10 X equal to -4 semicolon, Y is equal to 6. start is equal to 1 tick b1 semicolon, hash test start is equal to 1 tick b0 semicolon, and end module. So this is the code of the test bench. If you like the video, share with your friends. Please subscribe the channel and have a very nice day. Bye bye.